Welcome back to 8701. So the name of this class is called Casimir trick. But what we're actually going to do is we're going to evaluate or learn how to deal with spin information in the calculation of our matrix elements. So now what is it we're trying to do? So the first problem we might have is that we have polarized particles. So we have here again our example of electron-muon scattering. And if you assume that the electron and the muons are polarized, you will find, as we discussed in the previous lecture, that our matrix element is proportional to the joint vector of U1 times some sort of gamma matrix times the spinor, and we probably have a polarization vector as well included here to give the polarization of the photon involved in the as a propagator. Good. Now, in order to now get a number for m, we actually have to be explicit about the wave function of the external particles. And you can do this, you can just write this down. However, in experiments, we are often interested in the scattering of unpolarized particles. Even if you have a way to polarize a beam, your polarization is not going to be perfect. So in your calculation, you might want to, average or sum over the available spins of the particle. So now how are we going to do this? So we're trying to calculate the spin averaged amplitude. Why averaging? We want to average over the polarization of the incoming particles, again, because we don't know what the polarization states are. And we want to sum over the polarization of all final state particles, simply because each polarization state is a possible outcome of the interaction, and we have to sum over all possible outcomes. Good. So how do we calculate the spin averaged amplitude? So again, we start from our matrix element, where we have the joint vector, some gamma matrix, and our spinor. If you then calculate the squared of this matrix, we find this solution here. Great. And now we are just doing a few tricks. So first of all, we can write our joint vector U1 equal to U dagger 1 gamma naught, and then just continue this rewriting till we find this part here of the solution, which looks a little bit simpler, where we have now the adjoint matrix instead of the adjoint matrix given here. So we want to evaluate what this adjoint U1 gamma U2 is times adjoint U2 gamma adjoint U1. Okay, good. So this was just matrix algebra and working with gamma matrices so far. Now we're using this completion relation, where I probably haven't told you yet what this syntax here is. So gamma slash is equal to gamma mu p mu, and that's just a way to simplify writing down the equation. So if you use this so-called Feynman slash, you can also rewrite the Dirac equation in a simple form: I del slash minus m y equal to 0. That's now our Dirac equation. Remember, there was a gamma mu p mu here. All right, that's just a side remark. And we have to sum over all spin states, or the spin states of all both particles. Now, if we start with summing over particle 2, we can rewrite this here. We use this equation, this completeness relation, and just redefine this Q as equal to this part here. Okay, so now we have this equation here, which looks a little bit simpler because we just have our incoming and outgoing spinors for particle 1 given here. All right, now we're looking at this part of the equation now. And again, we're just doing a little bit of matrix algebra here. We find that this is equal to Q U1 U1 II, which is just simply summing over the same indices, which is the same as building the trace of this matrix. All right, so if you just put all of those together, you find that calculating the sum of matrix elements is similar to building the trace of a matrix. And then our final result is then given by this one. All right, so summarizing this part, we have a matrix element, and we saw that the matrix element is of this form, proportional to this form. And then when we try to calculate the spin average matrix element squared, that's equal to the traces of the particles involved using the completion relation. There's an additional additional factor 1/2 here, which comes from the averaging over the initial spins. So assuming exactly one of U1 and U2 corresponds to the initial particles, we find this factor 1/2. If both initial particles are the same, like in pair annihilation, then the factor is 1/4. And if neither is in the initial state, then the factor is 1/1, which you would have for pair production. Okay, good. So now we simplified the calculation of our matrix elements, putting the specific spin states in there and the specific polarization vectors toward the calculation of traces of matrices. So now we can look in what does it mean. So what is this is what Casimir's trick really is about. So summing over all spins reduces to summing over matrices. If you have antiparticles, the completeness relation reduces to P/-M. And then we can go ahead. So all you need to know now is how to deal with traces. So first, some general remarks on traces. If you have two matrices, A and B, you want to calculate the trace of A plus B, that's equal to the trace of A plus the trace of B. If you have a multiplicator here, a factor alpha, you can just take this out of the calculation of the trace. In those traces, two matrices commutate. The trace of A times B is equal to the trace of B times A. And then you can use this in order to show more complicated relations like this. Okay. Good. We have already started playing around with the gamma matrices. Here are a few more identities which might be of use when you calculate traces and you calculate matrix elements overall. The first one is this G mu nu times G mu nu is equal to 4. The anti-commutator relation we already discussed and have shown in one of our recitation. And if you have three matrices, you can rewrite them as -2 times the matrix which is in the middle here. Okay, so I'm not going through this in much detail here, but I encourage you to just follow those as an additional exercise if you didn't have the opportunity yet to play with those matrices. And then you can use those tricks, for example, the anti-commutator relation, to calculate the traces of, for example, gamma mu, gamma nu, which is 4 times G mu nu. Okay, so what you see here is that basically used this anti-commutator relation, put it in here, use this part here. This is basically 1, the trace of 1 is 4. So we get G mu nu times the trace of 1, over 4 times 4 matrix is 4. And so you get the trace of gamma mu is equal to 4 times G mu nu. Okay, and so on. Later on, we haven't discussed gamma 5 yet so much. Gamma 5 is defined as I times gamma 0, gamma 1, gamma 2, gamma 3. You will see when we discuss the weak interaction that there is a prominent role for gamma 5, this very special gamma matrix. And here are just some pieces of information for traces for gamma 5. The trace of gamma 5 is 0. The trace of gamma 5 times, sorry, a different gamma matrix is 0, and that's also true for the product of additional gamma matrices, which you can find when you just try to calculate this relation and this relation as well. Okay, one last piece of the traces with gamma matrices is shown here. Only with 4 or more gamma matrices can you define or find a non-zero trace involving gamma matrices. And here's one example where you have the product of 5 or 4 gamma matrices with gamma 5. And that's equal in this case to 4 times I times the total asymmetric tensor. The total asymmetric tensor is defined as -1 for even permutations of those numbers here, +1 for odd permutations, and 0 if there's two indices of the same. All right. Again, I'm not showing you this in too much detail, but I encourage you to, play around, and you will be asked in the homework, in the next homework, to play around with some of the calculations as well.